Hi, welcome to my video on why E is irrational. Now, there are many proofs out there for why E is irrational. You've probably seen one before. In this video, I'm going to show you my favorite one. So what we're first going to do, we're going to prove that E is between 2 and 3. This means that E is not an integer, which is really important. Because then in step 2, we're going to make our usual assumptions, i.e. that E equals P over Q, where P and Q are integers, and they have a greatest common divisor of 1. Then, using step 1, we know that Q cannot possibly be equal to 1. So that's the whole point of step 1. We're then going to consider the power series of E. We're going to multiply both sides by a clever constant, which we're going to see later. And after a little bit of manipulation and using a geometric series, we're going to have that an integer equals a non-integer, which means we have a contradiction. So let's get cracking straight into it. We need to show that E is between 2 and 3. I'm going to do this by integration. So what I'm going to do is I'm going to define I2 to be equal to the integral between 0 and 1 of x squared etx dx. Now by integration by parts, this becomes x squared etx minus 2x etx plus 2 etx between 0 and 1. This is the same as, well, plugging in the 1, we're going to have a 1e minus 2e plus 2e, so we're going to get an e. And plugging the 0 in, that's going to die, and we're going to be left with plus 2, or minus 2, should I say. Okay, next we're going to consider I3. I3 is equal to the integral between 0 and 1 of x cubed etx dx. Now, this we can again do by parts. This becomes x cubed etx minus 3x squared etx plus 6x etx minus 6 etx between 0 and 1. Now, plugging in the 1s, we have 1 minus 3, 6, minus 6, so we get minus 2, 4, minus 2, so minus 2 e's. Putting the zeros in, that's going to die, that's going to die, that's going to die, and we're just going to be left with minus 6 e to the 0, so just minus 6, but it's going to be plus. Okay, now where does our end conclusion come from? Well, etx is bigger than 0. X squared is bigger than or equal to 0 on this range. So we get that this is bigger than 0. Likewise, this is going to be bigger than 0. So we have two inequalities. We have that e minus 2 is bigger than 0, and we have 6 minus 2e is bigger than 0. And well, this gives us that e is bigger than 2, and that 3 is bigger than e. And we get step 1. So let's get cracking with step 2. So now that we've shown that E is not an integer, we can make our assumption. So we're going to say let E be equal to P over Q, where the GCD of P and Q equals 1, and P and Q are integers. And then using star up the top here, we've got that Q does not equal 1, and this is going to be important later on. So now, what we're going to do is we're going to write E in its power form. So E is equal to a sum from n equals 0 to infinity of 1 over n factorial, and that's equal to P over Q. Now I'm going to multiply both sides by Q factorial. This is going to give us a sum from n equals 0 to infinity of Q factorial over n factorial. That's equal to P. Now we've got Q factorial and we've got division by Q, so we're going to be left with Q minus 1 factorial, like so. Now, why have we done this? The reason being is the thing on the right, is an integer. Whereas what we're going to try to do is we're going to try to show the thing on the left cannot possibly be an integer. So let's have a go at doing this. So we're going to split this sum up into definitely integer and potentially not integer. So we're going to have the sum from n equals 0 to q of q factorial over n factorial. Now this part is definitely integer because the factorial on the top is bigger than the factorial on the bottom, which means the bottom is always going to be a factor of the top, so we're always going to have an integer. We're summing integers. Plus the sum from n equals q plus 1 to infinity of q factorial over n factorial. Now this part, we're not sure it's an integer or not. We're actually going to show that it's between 0 and 1. So we know that this here is an integer, and I'm going to say that this is m. So we get m plus the sum from n equals q plus 1 to infinity of q factorial over n factorial. Now next I'm going to write out some terms. So this is m plus, well, plugging in q plus 1, we're going to have a 1 over q plus 1 on the bottom. Q factorial over q plus 1 factorial. Next, plugging in q plus 2, we're going to have a q factorial divided by q plus 2 factorial. So we're going to have 1 over q plus 2 times q plus 1. Next, plugging in q plus 3, we're going to have a 1 over q plus 3 times q plus 2 times q plus 1. Now, I'm going to call this expression here r. Now, clearly r is bigger than 0. That's obvious. We're adding positive numbers together. So r must be bigger than 0. I'll just add on the dots here just to emphasize that this is going on for infinity. Now, what I want to do is I want to show that r cannot possibly be an integer. Usually when we want to show something cannot possibly be an integer, we want to show that it's between two integers. Specifically in this case, we're going to show it's between 0 and 1. But we need to prove that it's between 0 and 1. So I want to somehow evaluate this sum or find an approximation for this sum that's going to give us a nice upper bound. So what we're going to do is we're going to say that this is less than. Now, this kind of looks like a geometric sequence. So if I could somehow change this into a geometric sequence, we could find a sum of it. So I want to make each term bigger. That means I need to make the denominator smaller. So I'm going to change this to a q plus 1, this to a q plus 1, this to a q plus 1, and so forth. So that's going to leave us with 1 over q plus 1 plus 1 over q plus 1 squared plus 1 over q plus 1 cubed, etc. And well, this is a geometric sequence, so we can evaluate it. The first term is 1 over q plus 1. Then we've got 1 minus the common ratio, which is 1 over q plus 1 as well. And well, times in top and bottom by q plus 1. We're left with 1 over q plus 1 minus 1, which is equal to 1 over q. Now here comes our assumption that we made at the start. We said that q is not equal to 1, but q is an integer. So we get that this is less than 1. Because q is an integer, that is not 1. And we know that 1 over q is less than or equal to 1. So we have that r is between 0 and 1, which means we have m plus r equals, if we go up to the top here, p times q minus 1 factorial. This is an integer. This is an integer. But here's our break. This is not an integer. So we have a problem, we have a contradiction.